So by searching for the suprachiasmatic nucleus, CNN, or what we call the definitive point. Definitive means the ultimate, if you like, or the one and only point. And we were looking for a meridian imbalance with a person which was definitive, in other words, the most important one. And this cross-checked to the tissue extract of the suprachiasmatic nucleus. And when we tried to find out whether this was an acupuncture point, because it's in, what we found, it was in the midline, although it is on both sides, but it's within the hypothalamus, which is in the midline. So we found it wasn't on an acupuncture point as such, because GV20 is on the anterior fontanelle, or the bregma, and the lambda is GV19, which is behind, and it was about halfway. So it's right in the middle between GV19 and 20. So you could call it 19 and a half, or 19.A, whatever, but it's right on the top of the head. It's the highest point on the head. So that's the acupuncture point that we use for the suprachiasmatic nucleus. So this should not normally therapy localize because there shouldn't be a problem with it. It's the regulator of all the other circadian rhythms that go on in the body. If it therapy localizes, then this is an indication the person's probably got a sutural cranial fault. In other words, they've got a jamming of the suture, sagittal sutures there. So it shouldn't normally therapy localize. So if I could take somebody out as a patient. Jerome, do you want to pop out again? So what we'll do is we'll just test our patient here. So what we're going to do is we're going to get Jerome to touch on the area of the suprachiasmatic with 3 or 4 fingers, just to make sure you cover it. So you cover the exact area, and then pull up. Now, if that muscle goes weak, then this would indicate there's probably a sagittal suture, and then we would treat that with a respiratory adjuster. Now, what we're going to do now, so in relationship with AK, we talk about 2 points, a reference point and an object beam. So rather like a hologram, a reference beam, and a hologram. So in reference, the question is in reference to the definitive point, or the suprachiasmatic nucleus, how do you like, and then we'll go around the different meridians. So we'll go through the yang ones on the face first of all. So we'll do small intestine. So the question is, how do you like the small intestine? No problem. Then we'll do gallbladder. So how do you like the gallbladder? No problem. And then triple warmer. So you might like, as we're going through these, to just sort of say which neurotransmitter they're associated with. So all the yang points on the face are deficiencies. So small intestine is noradrenaline, gallbladder is acetylcholine, triple warmer is excitatory, stomach is, let's go back in there, stomach is histamine, bladder 1 is serotonin, these are all low, and then large intestine is low inhibitory. And then lastly, we count the conception vessel as a yang one here for low dopamine. So everything's fine here. Now we go to the yin points, which we include first of all governor vessel for high dopamine. So the yin points are always the high levels of the neurotransmitters. Kidneys high serotonin, lung is high inhibition. And then we've got heart, which would be high noradrenaline. And then we go circulation sex, which is high excitatory. And then we got 2 left. And this is where we start to sweat when you're on here. So you've got liver. And, so I thought we'd get right to the end. So the last one is the spleen 21, which is high histamine. Very popular, of course, to the people sneezing a lot at the moment because the pollen levels are quite high. So when the patient comes in, you can pretty much detect which one they're going to be. So here we got liver. And what we will find here, this is what we call the definitive meridian, was the ultimate one. And it'll be the same on both sides. So you get a definitive meridian on the right and on the left. But when we go to finding out the muscle associated with this, keep the elbow straight. What we do is we push the arm here down towards the right hip. So we're doing PMS. Ooh, go on, push. Okay. And then we'll do the one on the other side here. Push down here. Ooh, we've got a bilateral. And then if you pull the elbow in towards the side for the rhomboids. Okay, and elbow into the side for the rhomboids on this side. So it's a PMS bilaterally with him. Could we have from the neurotransmitter kit, the acetylcholine? So we will cross-check now that we're actually correct. You don't have to do this, but we'll correct because he's liver, therefore we'd expect him to weaken to acetylcholine, because acetylcholine will be the neurotransmitter that's in excess here. So we'll just get him up like that, ready for that. It'll be in the pain diagnostic kit, won't it? Yeah. It's in the pain diagnostic kit. Okay. So from strength, what we find is he weakens to acetylcholine, which is what we expected there. Okay. So if you put the slide back on. So what we've done is therapy localized, the CSN point should remain strong. Cross-therapy localized to each BE point. Only one will weaken. This is the definitive meridian. Okay. Now this meridian will not, or doesn't usually weaken in the clear. Well, so it's nice and strong in the clear without going to the central, the suprachiasmatic nucleus. So what we've got is a hidden, if you like, underlying problem, which we call a definitive, because it's the ultimate problem, both characteristically with the person, with the emotion, and also with the physical side. So in Jerome's case, he's got a weakness of the pectoralis major sternal, which basically pull the shoulders forward. Okay, so if you've got a weakness of there, what happens is your retractors will hold you back, won't they? Which is typical of someone with acetylcholine. Rigidity, isn't it? It's pride. So what happens is you get like this because the PMSs are weak, so the rhomboids and the middle traps and the lower traps are holding the shoulder girdle back. Okay. So let's go back to the screen. So you'll confirm with the respective neurotransmitter vial, which is what we did with acetylcholine, and identify the weak muscles. So that's found the meridian. Now let's have a play with that. So there's the yang points on the face and the yin points on the body. Yang points are always the indicate neurotransmitter deficiencies. Yin points are excesses. Now, we can use this to correct the body clock, because the body clock is the biological rhythm from the circadian rhythms of day and night, and we know that these work in 2-hour points through Chinese medicine. So the body clock has each 2-hour period when it has a greater energy than any other time. If we all have a look at our watches now and say it's about 25 past 2, it's 25 past 1. Okay, we're all in agreement because we're in summer saving time. So that's between 1 and 3, which is small intestine time. So it means that at the moment his small intestine time, which is there, the alarm point for the small intestine point will therapy localize positive if the body clock is set correctly. If it's not set correctly, then it won't. So what I'm hoping here is on small intestine time, pull, fantastic. He doesn't weaken. Okay. So that's what I was hoping. You stay back from it. Okay, let's just touch it with the other hand. Are you right-handed? Yes. Yeah. So usually what we do when we come to correct it, the patient touches the alarm point or the body clock horary point, as it's called, or the now time, with the right hand if they're right-handed. Okay. Now, if they do the correction, they tap with their left hand. But if you do it, you can tap with the right hand. So you hold that, and I'm going to tap now the suprachiasmatic nucleus, the back part of the head. They're right on the vertex or the top of the head, about 60 times at 2 hertz or twice a second. In the other way that we did GV20, if you remember, but we did the opposite to the now time, the one time on the capillary meridian. This is quicker. So you actually touch with the right hand the now time of what it should be now, and then you tap on GV19.5 or the suprachiasmatic nucleus. So you can do this yourself as you cross over the time zones or when you land wherever you are. But I have a piece of paper sheet that I give to patients to tell them when to do it, usually at 6:30 in the evening, wherever they are, because 6:30 is kidney time. And wherever you are in the world, it's always the same. So even if it's summer saving time, it's still 6:30. It's 5:30, which is still kidney time. But if you know where your acupuncture, where your now time points are, the alarm points, you can do this at any time you want. So it resets it. So the ideal for this is to relieve jet lag. But if your body clock is not set correctly like yours, then what will happen is a lot of the testing that we will do won't give us the right time. You know, he won't necessarily show up to things because he's not in Greenwich Mean Time, but he is now. Okay, so let's go back to the screen. So now time. These standards are standard time, allow 1 hour advancement in the summer. Therapy localize the alarm point for the current or horary meridian. A strong muscle should weaken. If it does not, then the now time is not correct. Right-handed people should therapy localize the now point, and either the practitioner taps the suprachiasmatic nucleus point or the patient taps it with their left fingers 60 times twice a second. The reverse holds for truly left-handed people. So this is an ideal technique. This is an ideal technique that you should learn for yourself and also for your patients, and you should test the now time with people as a routine before you start getting into patients' problems. Okay. So let's talk about something very different now, how to stimulate the brain. We introduced the work of Francis Crick this morning with his work with fiber optics, when he found that neurons would be attracted towards certain colors or wavelengths and repelled by others. And then he took that big step to saying that he could turn genes on with certain wavelengths and turn them off with other ones, which was a big move, and that's what he called optogenetics. So optics being the eye or vision, related to genetics. So genetics could be switched on and off. And since that time, people all over the world have been treating traumatic brain injury with using lasers. And the advantage of the lasers is they penetrate quite deeply. They can go up to 5 or 6 centimeters deep. But in really recent years, the advent of powerful LED light bulbs has also matched, or virtually matched, the power of the laser in the depth. So a powerful LED with the right lumen can penetrate up to 5 centimeters, which is 2 or so inches deep, which is quite some depth. What I found was a mystery is different neurologists and people doing this work didn't really know what wavelengths to use. It was very much trial and error. And there were certain wavelengths which were sort of very popular. 880 seemed to be very popular with lasers in the near infrared zone. 630, 660, 670 has become very popular with NASA for treating injuries and things. 450, 460 has become very popular for treating infections. So there's a range of different sort of lights and colors, LED and in lasers. The advantage of lasers is you can pinpoint it precisely with a very small monochromic light. In other words, if you put 670 with a laser, you get 670 hits the spot. Whereas if you use an LED, you'll probably go quite a few nanometers either side, maybe 5 or 10 nanometers either side. So you could be getting 660 up to 680. So it's not as precise, but it's a lot safer. So people, when they use the lasers, the patient and the practitioner have to wear special protective goggles. So in other words, they can be quite dangerous if accidents happen. So the LED is much safer for us to use and considerably cheaper. So when I started looking into this, the journey went back really 20 or more years ago, when I first did a seminar in Bath, probably 25 years ago now, on detoxification. And I learned most of what I learned from Harper's Biochemistry, as I still do, on their section on detoxification. And we learned that there were 2 phases with detoxification, what's called a phase 1 and a phase 2. And phase 1 was to hydroxylate or make the substance more water-soluble, and phase 2 was conjugation with things like glutathione, etc. But the phase 1 was a series of enzymes or family called cytochrome P450, which I'm sure you're all familiar with. And basically the object of cytochrome 450 is to put an OH molecule onto a poisonous substance and to make it less poisonous, but to make it more water-soluble so the body can start to pass it out. And I remember reading about this 450 and that it produced a wavelength of 450 on gas chromatography, which is a system of measuring the output or the spectroscopic emission of various substances. And then I put it away and didn't really read it again for 20 or more years. About that, the penny didn't drop, and sometimes that happens with me. You know, I get a bit of information and then I leave it and chew it over for 20 years in the subconscious somewhere, and then suddenly, boom, it comes up and I think, oh, yes. And it suddenly dawned on me, 450. Cytochrome 450. Why is it called cytochrome 450? I know 450. 450's blue. And what I then reread it is, and it was very interesting because it says cytochrome P450 was picked up, the wavelength of cytochrome P450, when the cytochrome P450 enzyme was exposed to carbon monoxide. So in the presence of carbon monoxide, cytochrome P450 emanated this blue color of 450 nanometers. And of course, 25 years ago, I didn't really understand too much about that. But now I thought, I can make that. So on a computer, you can make anything from wavelengths and you can produce the colors out there. So I thought, oh, I'll do that. And so that was the result. This is pretty much mid-range blue. So quite a pretty one there, carbon monoxide. And I thought, yeah, if that's cytochrome P450 links with this, locks onto that, we should be able to test a person with cytochrome P450 or this blue if they've got carbon monoxide poisoning. So I have a sample of carbon monoxide, a vial, and I found that a few people do actually weaken to carbon monoxide, not because they're being poisoned from carbon monoxide outside, but from carbon monoxide inside. Because we actually produce carbon monoxide in the mitochondria when we start to break heme down. And heme degrades into giving off carbon monoxide on its way to making biliverdin and bilirubin. And what I found is that people who did weaken carbon monoxide also weaken to the 450 acetate. Now, if you are in a state of hypoxia and you're breaking heme down, not only do you produce carbon monoxide, but you also produce cyanide, which is a pretty toxic substance. And cyanide is being used as a marker for problems in complex 4 in the mitochondria there for many, many years as a toxic substance there. And so if you show to cyanide, it's an indication you've got severe hypoxia. And when I looked after that and we went through that, what cyanide produces is 430. So if you look very carefully at the screen of the blue, I'm going to go back to the other one. You'll see the difference in the blue? 20 nanometers difference, but hardly detectable to the human eye. Very small, fine difference. There we go. See? As we get to 430, there's a slight bit of red comes in there, isn't there? Let me go back again. See, that one's almost a mid-range blue. And then we go to 430, and you've got a touch of red coming in there, just a very, very small amount. So 430 was a slide that we could use as an indicator if a person had cyanide poisoning. So this was really interesting, and I thought, well, I wonder what else we could do. Okay? So I got involved with looking at then different colors, and I studied it in much more depth than what I've done before. And what I learned is that the red end of the spectrum comes from about 640 nanometers, 645, all the way through to 770 nanometers, when we don't see it anymore and it goes into infrared. It disappears into total darkness over here. So beyond here exists, but we can't see it. Okay? We can feel it because it comes out as heat, but not as light. So down here we feel heat, like on a summer's day, and we see it as light. But as we go into here, it's more light rather than heat. And this end can be actually quite cold. On the other end, at 385, is the end of the visible spectrum for most of us. So when you get below 385, you go into ultraviolet, which again, we can't see. But certain people can see it, particularly people who've had cataract operations. So when they have their lenses taken out, for a while, they're able actually to see a little bit into the infrared. So they see violet colors, which we can't see. But most of us finish at 385. So it's a very short spectrum, just 300 or so of visible spectrum of what we can see. But from 645, where red begins, true red begins, right the way up to 770, it doesn't change. Red is red. We can't see any difference. Although the wavelength changes, it's to the human eye, red is red. So we can't produce anything between there apart from red. It's only when we lose that 770 that red disappears basically into black. So looking at red, you can get dark red and you can get light red if you add black to it or white, but you don't change the red. The wavelength of red can vary, but the picture that we see of red remains the same. There's no variation. But when we come to blue, we've got a third of the whole spectrum is blue. So as soon as we get to turquoise blue, there's subtle changes. Every nanometer produces a slight little change, as we'll see. So that's the human spectrum. And of course, what's interesting is what's over here and what's over here. These are the investigating parts. So if you want to make these colors, you see there's 645 where on the computer, red is red. So up to that point, we've got yellow and orange. So we're bringing in a little bit of green with the red. You'll notice the blue is 0 at this point here. So as we come from the green area here, we go through yellow and orange. And where that disappears at 645 is red. So to be able to print this, we can only print red. Red, 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 right up to 608. The human eye, presumably some animals can see into red with different distinctions, but we're unable to. Our cones are set that we can't actually detect it. Therefore, we can't make acetates, which is frustrating, between 645 to 700. So we don't know. So we have to block those all together and say, right, red is red. It covers us for the whole lot. So if a person weakens to the red acetate, and then it's all of that particular wavelength band. So if we go back to the original investigation some 15, 20 years ago, when we looked at colour as a diagnostic tool, we first of all took the 7 colours of Isaac Newton's spectrum, and each acetate wavelength was printed from mid-range figure for each colour. So when we came to, let's say, blue, we took mid-range blue, probably about 450 nanometers, but we didn't take into consideration what happened to 430 or 480. Okay, we just took the mid-range one. And I didn't realize we made a mistake at that time because we were only looking at specific wavelengths. So we didn't always get people to weaken to one specific color. They could go right through the whole lot. But they could have been a blue, but they might have weakened not to 450, but to 430 or 480, you see. So then we put the complementary colors, or the opposite to these, and we came to the conclusion generally that the complementary colors would represent the yin meridians, and the ordinary fixed middle ones would be the yang meridians. So gallbladder, for instance, is coupled with the liver. So blue, the complementary color to blue, would be yellow. And therefore, yellow would be a complementary color to blue, and blue to yellow. But again, that didn't work in all cases. It worked very well when we used light boxes for people with depression and things. But you couldn't guarantee, say, with Jerome, who showed up to being yellow, he showed up to be the liver, that he would weaken to mid-range yellow every time. So we needed to be a bigger range of yellows. So we needed to get our yellows from the beginning of where yellow was to the end to be much more accurate with our tools. We are used to the 3 diagnostic constitutional body type colors of red, green, and blue, which is what the human cone sees. And we've been using these for many, many years. But this is to do with light coming from outside, going through the acetate into the eyes. And what we found, as we'll demonstrate in a minute, is you can actually move that, or you can shut the eyes and the people still weaken to it. But if you put that color underneath clothes, it doesn't weaken anymore. But when the clothes are off and the light is coming through from outside, which indicates the challenge that we're doing is actually from outside in, which are called packages of light, or photons. So that's what we use there. And then I started to look at biophotons. And a chiropractor friend who used to come on the seminars many years ago, I think he's emigrated to South Africa, called Philip Sykes, sent me some technical data, reams and reams on this, of the works of Fritz Popp, the German physicist in the 1960s and 70s. And it was all about the structure of DNA and the frequencies and how this was affected by color. And it was quite hard going because he was a mathematician as well as a physicist. But I did manage to get through it, and I thought, yes, I begin to get to understand this. But he took his work from Alexander Gershwitz, who was a Russian biologist, which we'll look at in the 1930s. And soon after that came a very interesting person called Dinshaw, who started a system called spectrochrome in America, where he claimed he could cure all sorts of ailments by different wavelengths of light. Interesting, everything except broken bones. I don't know why he put the exception on broken bones. But he made some pretty big claims, which, of course, the FDA didn't like very much. So they destroyed most of his equipment and locked him up. But with rereading his work, it's really quite interesting. and perhaps forms the basis of quite a system that we can use with kinesiology. Because remember, back in these days, in the 1940s, 50s, can you imagine people didn't use kinesiology? How did you do the work without kinesiology? Amazing, isn't it? So Pop was really the father of biophotons, in other words, light coming from within. And what he was able to measure with amplifying units was what this low level, as he called it, of luminosity that came out of the human being. And that the low level of luminosity could be amplified with special equipment, and that you could see it. And he put people into pitch dark rooms. Then they used this camera to amplify it, and they saw this light coming out of the body, which varied in its intensity in 2-hour periods, which was really interesting, isn't it? 2-hour periods, in other words, it went in time with the meridians as the different organs. It didn't change color, which I thought was what would happen, that it would actually change its color during the 2-hour periods. It changed its intensity, but they did observe there were different colors that came out. And that he came to the conclusion that the color that comes out should be the same color as we see in the air, and that was white light. If you saw a color coming out of a person, it was an indication there was a problem. They didn't know what the problem was, and it was only fairly recently that we think we know what the problem is. Why is it that some people emanate red out there? But we know that a perfectly healthy person, if there was such a thing, would probably emanate a white light. This is why whenever you see depictions in pictures of Jesus, you don't see him with flashing red or green lights coming out of him there. There's always a white light that comes out of a person. So a person who's in total harmony and presumably totally healthy would emanate a white light out of them, which would be a light, not white, but it's a clear light, like the light from the sun. Now, our friends Philip Walpole and Hilary Pittman, who are practitioners, took this work up some years ago, and they developed some concepts themselves, very interesting through the years, from Philip Sykes' work also. And of course, in more modern times was the work of Francis Crick, that clicked from a neurobiologist point of view. Now let's go back, because it starts to become more practical based now. So Pop chose to work, this is Fritz Pop in the 1960s, chose to work specifically with ultraviolet light because of the experiments of a Russian biologist named Alexander Gertwitz, who, while working with onions in 1923, so this whole story is based on onions in 1923, he discovered that roots could stimulate a neighboring plant's roots if the two adjacent plants were in quartz glass pots, but not if they were in silicon glass. The only difference being that the silicon filters out ultraviolet wavelengths of light, while the quartz did not. Gertwitz theorized that onion roots could communicate with each other by ultraviolet light. In other words, light was a form of communication between plants, and maybe between cells, as we'll learn, not just in plants, but in all living creatures. Now, what Pop discovered was that, and then he used a series of chemicals. Now, the first chemical that he did was called benzo-A-pyrene. This is a very, very toxic substance. It's usually found in soot, so which makes it a carcinogen, basically. An area where Joe Schaefer and myself first went in Russia, in Novokuznetsk in central Siberia in 1991, I think it was, had the highest level we discovered afterwards of benzopyrene in the world, because it was full of these tall smokestack chimneys pumping out the blackest of smoke. So you imagine all that in your lung. But there's two types of benzopyrene. There's the A and the C. So benzo-A-pyrene, the cancer-producing molecule, absorbed the ultraviolet light, then re-emitted it at a completely different frequency. Okay, in other words, it scattered the light. It was a light scrambler. The benzo-E-pyrene, harmless to humans, allowed the ultraviolet to pass through it unaltered. Interesting. So something which was not carcinogenic took the light and let it pass through, but something which was carcinogenic took the light and dispersed it, scattered it. Okay. Pop was puzzled by this difference and continued to experiment with ultraviolet and other compounds. He performed his tests on 37 different chemicals, some cancer-causing, some not. This is back in the 1960s, 1970s, because there weren't so many cancer chemicals around, which were known of then. After a while, he was able to predict which substances could cause cancer. After a while, he was able to predict which substances could cause cancer. This is quite devastating, isn't it? That he was able to, all those 40, 50 years ago, to tell that a substance could cause cancer or not. After a while, he was able to predict the compounds that were carcinogenic, took the ultraviolet light, absorbed it, and changed or scrambled the frequency. Each of the carcinogens created only to reacted only to the light at a specific frequency, 380 nanometers in the ultraviolet range. Okay, so let's have a look at 380. That's 380 nanometers. Now you can't see that, can you? You say, oh yes, I can see a violet. You can't. You can see what appears to be a violet one. And the other week we were in taking the children at half term to the London dungeons, and in the dungeons in there, they have these ultraviolet bulbs. Okay? So you look at the ultraviolet bulb, and it looks violet. It looks the same as that, doesn't it? So what happens is it looks a violet sort of colour. And then you look at your shirt, and you've got white flecks all over it. Okay? And then you put your teeth like that, and hopefully your teeth glow white as well. Okay? But there's no violet light between that bulb and you. It looks dark, doesn't it? It's just the same as any light coming out. You don't see violet between there and there, but that's where the ultraviolet's coming through. That's why what you see is the filter where it comes through, the light comes through, which then produces ultraviolet, but you can't see it. So it looks like any other light, but it's ultraviolet. And you see where it lands on your clothes, right? That's why you can't see that. That is the colour of the bulb, if you like. So by making an acetate of that, it'll come out that colour, but you won't see the light that goes through it. Do you understand? Right? So although it's beyond the human spectrum, it doesn't matter, because it's the light in between the two. So if we could get a 380, now what I want to show you is a carcinogen and how you can tell it. And the simple way is to get a plastic bottle. We don't want to take that one because you've got stuff in it. Is there an empty plastic bottle? Anybody got an empty one, ideally? I'll take... the softer one is what I were after, really. Okay. Do you want to pour the water in a glass temporarily? You probably won't want to drink it again. Well done. Is it empty? Yeah. There you go. Okay. Right. Jerome, you're back. You got the acetate? Okay. So, right, down onto your back. What we're going to do, first of all, is we're just going to show you that we're going to just take a strong indicator muscle. We're going to show you a potential carcinogen. Okay? So we all hear about the evils of bisphenol A. So Jerome is no problem at all with the bottle. Okay? Now what we're going to do is we're going to put the 380 on him, just to make sure he doesn't weaken to the 380. Okay? And now we're going to put the two on together. Okay, do you want to just gently hold that? Okay? And this is what is horrific is... Okay, now would you want to drink out of that again? Okay. Now, this is interesting because according to Pop, this would be a carcinogen. Okay? Now, we found since that time certain things, and you can play with this now for all the rest of your life, testing out chemicals with people. But we found that there are certain substances which weaken everybody. And it's this soft, crinkly plastic, all right? You haven't got a problem because you don't weaken to it in the clear, all right? So it's not an issue with you. It doesn't matter who I choose, all of you will weaken to the same thing if you use this and this. It's universal. So this is a carcinogen to everybody, the bisphenol A, which is well known. But it doesn't mean that it's a problem for you, right? Unless you weaken to it in the clear, in which case you've got an overload of it. So it's not an issue, but it is. Now, if we change this for something else, okay, so what we could do is we could use the 4-hydroxyestrogens. Okay, so estrogens or estrogens are natural substances in the body, but we know we detoxify them through different pathways, the 2, the 4, and the 16. And we all know that the 4 are the bad ones. We should try and shift it through the, for the 2 to reduce the amount of xenoestrogens which are in the environment. So we need a hormone kit there. Okay, so what we're going to do is we're just going to have a look. And we need, remember this is the 4. Now the 4-hydroxyestrone and the 4-hydroxyestradiol are the bad ones. Okay? And these are mostly bad for the girls in the way of breast cancer, and for the boys with prostates. Okay? But particularly with the boys is the 4-hydroxyestrone, and also the 16-hydroxyestrone is bad for the boys. Okay? So if you get me those out, 4-hydroxyestrone. Okay, remember the two are the good ones. 4-hydroxyestrone. This does not mean you've got a problem, right? I'm just demonstrating to show you these are all potentially carcinogenic. So 16-hydroxyestrone, that's the bad one for the boys. That's the one that causes the prostate problems. And then the 4-estradiol, particularly for the girls with the breast cancer and other hormone-dependent cancers. Okay. The other one which surprised us completely, took us quite by surprise, is pregnenolone. Pregnenolone is the precursor substrate to progesterone. And pregnenolone is a very genotoxic substance for both males and females. Okay? So we want to get rid of excess pregnenolone and allow the natural progesterones to then go on and metabolize into the other steroid hormones. Now you can go on. We found radium, not surprisingly, probably any radioactive material. When we did this in Ireland the other week, they suggested perhaps what about aspartame? And what about monosodium glutamate? You know, you can go on and test all sorts of things. But it's a bit of fun, but it's not just fun now because you think, ooh, I've got a patient who weakens to 4-hydroxyestradiol. What do I do? And you realize that they've got a toxic problem. Now, an interesting comment from somebody in Ireland was, does that mean if a person weakens to 380 in the clear, that they've got a cancer? And it made me think, and I thought, ooh, because I found people of my patients who show to 380, and then sometimes I do a workup, and then they would show to 380 at the end of the workup. The answer is no. It tells you if there's something genotoxic which has altered the structure of the DNA, which of course we all got them, called mutations or single nucleotide polymorphisms or SNPs. So we've all got these. We all inherited these, unfortunately, from mum and dad, and we may have acquired ones ourselves during a lifetime. So 380 is an indication of the genetic structure of a person, which is altered by a toxin, a genotoxic substance. So let's just have a look here. So these are the substances that we found universally weakened. As I say, it would be nice for you to do the research yourself on substances, and then let us all know which ones you find so we can all test them. Let's bank them in, because you may find there are a lot of chemicals out there which are not known as carcinogens, but we can identify them using POPs procedure there. So what I want to just get a couple of definitions there. This is not in your manuals, but these are, you can do this. So genotoxicity in genetics, genotoxicity describes the property of chemical agents. That's fine. That damages the genetic information within a cell, causing mutations, which may lead to cancer. So in other words, not all genotoxic substances lead to cancer. What he found was a genotoxic substance, something which damages the gene and leads to a mutation. This does not mean that they all turn to cancer. All right? So the 380 is not a marker for cancer. It's a marker for a genotoxic change or mutation. While genotoxicity is often confused with mutagenicity, all mutagens are genotoxic, however, not all genotoxic substances are mutagenic. In genetics, a mutagen is a physical or chemical agent that changes the genetic material, usually the DNA of an organism, and thus increases the frequency of mutations above the natural background level. As many mutations can cause cancer, mutagens are therefore also likely to be carcinogens. But it doesn't mean, well, I want to make it very clear, if a person weakens to 380, because there'll come a time when you all weaken to 380. Okay, when you've cleared out what it is with the body in the physical as you are at the moment, you then would enter into the genetic makeup of a person. So when a person shows weak to 380, it's an indication they want to talk about the genes. And we'll talk about how you do the treatment for that and what sort of things will help balance that as we go through in the next hour or so. So that's 380. So you'll enjoy using that and try the hormones, particularly the 4 and the 16 hydroxyestrones and estradiols, the bisphenol A and the pregnenolone there. Okay, let's have a quick look at reactive oxygen species. These are sometimes called free radicals, although not all reactive oxygen species are free radicals. In other words, they don't have unpaired electrons on the outer orbit. We know here on the right that we produce a certain amount of free radicals or reactive oxygen species from normal mitochondrial oxidation. So as we produce energy in the mitochondria, a certain percentage, anything up to 5% of oxidative reactions, will produce superoxide. The respiratory burst, this is when our white cells increase their production of superoxide when we have an infection. So we need to increase our body temperature. This increases our rate of respiration in the cell, which produces increased amount of free radicals, because we need those free radicals to kill infections. Okay? If we didn't have free radicals, we'd never kill any of the first bug that came along. Phase 1 detoxification. Every poisonous or xenobiotic that goes into the body, every molecule produces one molecule of superoxide. So this is why people look and age quicker in toxic environments. Okay, so one molecule of a toxin or a strange substance, which includes drugs, because all drugs are xenobiotics and have to be detoxified, will eventually cause free radical damage. And hypoxia, what we know as low tensions of oxygen, is probably the biggest stimulator of producing reactive oxygen species. Or hyperoxia, when people go into diving bell chambers and that's not often. So superoxide is probably the least inflammatory of any of the reactive oxygen species. But it's there for a reason. It's there to kill microbes. And this is normally reduced by superoxide dismutase to hydrogen peroxide, which is not a free radical. Hydrogen peroxide is a reactive oxygen species. If you spill it on your skin goes white, so it's basically a bleaching agent. And then we reduce hydrogen peroxide to water. So this is the clean machine, if you like. Now, in the presence of iron and copper, free iron and copper, hydrogen peroxide will reduce to hydroxyl radical and to singlet oxygen, which are very reactive oxygen species and damage a lot of the DNA rungs. Or we can shunt hydrogen peroxide this way through an enzyme called myeloperoxidase into making hypochlorite and other halogen hypos. This is known as household bleach. So household bleach is hypochlorite. And we need the hypochlorite to kill a lot of gram-positive bacteria. And from our clinical testing, it's the one that most malignancies are killed by is hypochlorite. So we want hypochlorite, but on the other hand, we don't want hypochlorite when we don't need it. All right? Otherwise, you imagine putting bleach, as I tell people, bleach into your knee joint, you're going to do some damage to your cartilage. So anybody who's got a high level of hypochlorite when they don't need it has a lot of bleaching going on. So on the other side, we have nitric oxide, which is produced from the amino acid arginine by inducible nitric oxide synthase. And when nitric oxide non-enzymatically comes in contact with superoxide, they form the dreaded peroxynitrite, which is the most reactive of all the reactive oxygen species. So this is the most reactive as far as inflammation and damage. But this is to the real hardcore viruses in the body and fungi. We don't usually produce peroxynitrite unless you've got a real resistant bacteria or problem, unless you've got high levels of nitric oxide and superoxide being produced. So that's basically the family of the reactive oxygen species. Now, the normal way you get rid of these reactive oxygen species is with the enzymes. Superoxide dismutase here, catalase here, and glutathione peroxidase and other peroxidasing enzymes. Take it down to water. That's the simple part of it. Now, I've underlined these enzymes, and these enzymes are heme-dependent enzymes. That means they've got this ubiquitous substance called heme in it. And heme is this substance which is light sensitive. So all these enzymes here, inducible nitric oxide synthase, mitochondrial oxidation, in other words, all our cytochromes, phase 1 detoxification, which is your cytochrome P450, myeloperoxidase, which is needed to stimulate the production of hypochlorite, catalase, which is needed to reduce hydrogen peroxide to water, and the other NAD, H peroxidases and other peroxidases, again, are all heme dependent. So heme means they're light sensitive. So we know we use these to kill microbes. Now, according to Bruce Ames, each cell in the body suffers between 25,000 and 100,000 oxidative hits per day. So free radicals aren't something you eat because you eat a packet of chips. Okay? They are being produced by those four main mechanisms in every cell. That's an awful lot of repair. Okay? That's a lot of damage to every cell. And remember, the repair has to, particularly the repair is to the DNA, has to be by DNA polymerase, which is a zinc-dependent enzyme. So this figure is obtained by measuring the quantity of oxidized deoxyguanosine in the urine per day and dividing it by the number of cells in the body. That's why there's the variation.